I'm going to go through dead load and how do we estimate dead load and what is dead load. Probably we have time also to cover live load in details. And I think by the end, we will start the snow load. So dead load is our first load. It's covered under the code. What you see on my screen is just a snapshot from the Alberta Building Code 2019. And if you guys remember, I asked you the last class to be or to download it and have it on your machine. Now, I guess the first thing is we need to set and define what makes a dead load. Because sometimes, trust me, you think it's easy, and sometimes, you think it's straightforward, and this is dead load. And so, for example, if you have a building and this building has a podium, people in summer they go outside and they enjoy, and on this podium there is barbecues and there is some planter for some plants. What do we consider those planters? Do we consider them as live load or dead load? And some of you will say, okay, it doesn't matter. No, it does matter, because if you guys remember from the load combination, live load and dead load, they are treated differently. We multiply them by a different factor. If you guys remember from last class, the 1.25 and 1.5. So we have to be careful and specify or know whether this specific item belongs to a dead load or a live load. Anyway, the code is trying to give us a hand here, and I'm gonna let you guys read the item 4.1.4.1 on my screen. I will mark it for you, so I want everyone to take 2 minutes, 2 minutes to read this item here. This item simply tells you what is or what are the things you should consider as dead load. And I'm asking you to read only statement number 1. So please stop in here. Okay, so I'm gonna draw a box around what I want you to read. Here we go. I want you to read now this part. So I think that's enough. When you start reading about what constitutes a dead load, is simply number A. Number A is the weight of the member itself. The weight of the member itself. In my classes, I'm gonna always refer to this as self weight, member self weight, and this applies to slabs, applies to beams, applies to columns. And in my class today, you will learn in details how do we estimate that number. Number B, the weight of all materials of construction that will go into the building and be supported permanently by the member. And I guess when we say that, we're referring to, for example, if you have a layer of insulation, if you have like a membrane, if you have a ballast or some stones, or if we have like, for example, flooring material. So all those things, they are not the self weight of the member. However, they will be permanently supported by the member. Number C, which is very important, the weight of the partitions. The weight of the partitions. You guys know that if you think about floor plans, you will see on the floor plans, we don't typically leave the space open, except for things like classrooms. However, if you have, for example, your house, we need to split the area into different like kind of use, like bedroom and kitchen, stuff like that. So we do that using partitions. So partition walls are as well can be considered as a dead load. We will have more discussion about partition loads in the next discussion. Number D is the weight of permanent equipment. So if you have equipment like, let's say, mechanic equipment like a boiler or something, then this is considered as a dead load, not live load. A dead load, not live load. And then finally, the vertical load due to earth, plants, and trees. If you guys remember my example of the podium, if you have a podium where people they go in summer and enjoy the weather, so in this case, the planters, the earth, like the soil, and the trees, the three of them are considered part of your dead load, not live load. Now, there are some other statements, and you can see in my slide here, we have still 5 statements to read about dead load. Okay, gives you more details or maybe some exclusion about what we learn in number 1. For example, if you think about the partition load, okay, so when you read statement number 2, which I don't want this to turn into kind of a boring and reading class, this is the code, and in this part here, we need to extract a very specific information that we can apply to our design. Okay, so for statement number 2, it says except as provided in statement number 5. And reading the code, so I guess you read the code in other classes, but reading the code is not really a straightforward process. It's tricky. One of the things that kind of tricky is when you read the statement, you have to be very careful. For example, look at statement number 2. Start with the word except. So it creates an exception. And guys, here's my advice for you. As soon as you come across the word except, then stop. Don't continue. Don't even continue reading except like the statement number 2. Because if it refers you to statement number 5, then right away, you go from number 2 to number 5 and read and understand what are the exceptions or what's the exception. So I'm gonna go to number 5 because number 5 is something students they have hard time to understand. It says number 5, in case where the dead load of the partition is counteractive, the load allowance referred in sentences 2 and 3 shall not be included in your design. Oh my God! Wow! It means in some cases, which is some exceptions, we need to ignore the weight of the partition. And what are those cases? Counteractive. Okay, let me wake you up. Let me wake you up. Anybody in this class can give us a case where some load is counteractive, or tell us the meaning of counteractive? If you know the answer, please show your hand. Still sleepy? Sunny, go ahead.
Yeah, so it's like counteractive load. So it's like uh, two different load which like denies each other. It's like seismic load and the load that a foundation give on the earth. So it's like that kind of load. So it is like that both load uh, like oppositely denies each other and support is like each other. Like while the foundation puts pressure on the earth and the seismic load like gives support to the foundation, something like that, sir.
Okay, thank you. So although what you said is maybe partially correct, but since you are my first client this morning, I will give you two marks. So 2 marks for Sunny here. Okay, so
Thank you, sir. Thank you very much.
oh, no problem. Oh, no problem. Okay, so okay, guys, look at this. I'm going to show you right now as what we mean by counteractive. And so let me show you. Let's say this is a cross section of a building, and so this is the ground here. Okay, so this is the ground. And guys, look at this. When the building is hit by some wind or seismic loads, okay? So let's say here I have some wind load hitting the building this way. So you can see this wind load, I'm gonna mark it here as W. So this wind load here is simply trying to kind of tip the building over. So simply it's trying to tip the building over around this point here under the wind. Okay, so for example, if there is not enough weight of the building, this is what's going to happen. I'm going to show you what's going to happen here. So here is my, I don't know if I can rotate of this guy, but you guys get the idea. If I'm not able to rotate this in this PDF here, but you guys think you are thinking that the building will simply tip over if there is no counter for active force to stabilize the building. So my question for you guys is, what really stops this building from tipping over? Any help? So the wind or the seismic load is going to hit the building laterally. So what happened is trying to tip, okay, turn this guys over, okay, around this point. So what stops this building from tipping over? Any help?
You said the counteractive partition?
No, tell me what exactly like is trying to stop the building from tipping over.
Okay.
Okay, so let's go with Martin. So get some other people to say it.
Isn't it like a combination of the self weight of the building acting on the right side if the wind is coming from the right, and that connection on the bottom right side, I guess? It's just the way I think about it.
Okay, let's see next. So next is Siham.
Yeah, basically, I think it's the actual concrete foundation, because the building is connected like underground. It's not just floating on top.
Okay, let's see next. Muhammad.
Would we need some type of moment connections there to stop the rotation? So maybe it's fixed down there.
Okay, thank you. Let's see next is Jelly. Jelly.
Is it the retaining wall in the under the foundation?
Okay, thank you. Next is Hamid.
Wouldn't it be like shear wall for elevator shafts or something like this? Or for stairs cases?
Yes, like so guys, let's stop at this point. So you guys are trying to say something, but I think the closest is Martin. So Martin is saying the weight of the building. I'm going to show you here an arrow. So if I draw here an arrow, and so this arrow here represents the weight of the building, and you can see around this point here, the wind is trying to make a moment around this point, and you can see the weight of the building is counteracting the action of the wind. So now I'm asking you, let me ask you, I'm a designer, I'm trying to study the stability of this building for overturning, and now we can see this is subjective, right? Because this is the gravity loads on the building, which includes the snow, it includes the live load, includes the dead load. Okay, let me ask you one by one. Should I, when I study the stability of the building, so I want to make sure that the building will not over tip under the wind or the seismic. So my question is, in my analysis, I'm going to say this one here, I'm going to say F, in general, force F. I'm asking you, do you think when I estimate the load, like the F, the force F, should I include the snow load? Please raise your hand. Muhammad, go ahead.
Oh shoot, I forgot to unraise my hand, but I think you don't factor in snow load because snow load is coming and going.
Thank you, sir. You get for that, you get 2 marks. So we have 2 marks for Muhammad and we have 2 marks for Martin. Okay, so that's true, guys. Look at this, please. When we think about load, like the force F, you shouldn't include the snow, because the snow is counteractive and there is no guarantee that the snow will stay. Okay, so sometimes we have a storm, like windstorm, and we don't have any snow, which means it is not really in our best interest to ask the snow to help us to stabilize our building. Okay, next is, should I use the live load in the calculations of force F? Please show your hands. I guess um, we have Domenico or Dominic.
You shouldn't use it because same thing, it's always changing.
Okay, so that's why I'm going to give you only 1 mark. I'm sorry for that, but there are lots of marks. Don't worry about it, okay? Okay, so now we're heading to our last the question is, I'm asking you now, obviously there is only one thing left for me, dead load, because we said that dead load exists and always exists. So I think this is my last backup to think about it. So when I study the stability of the building and trying to see what can counteract the wind. Obviously, the dead load, it doesn't go anywhere, it stays, which means I can rely on this force to resist the wind load. Now, let me ask you, since we said the partition is part of the dead load, should I include the partition in the calculations of the force F? Show your hands if you know the answer. Okay. Sunny.
Yes, please. Because it's part of the building.
Okay, thank you, sir. So let's say Jelly.
No, some of the partition that doesn't counteract to each other, then yes. But otherwise, if they are counteracting each other, then don't.
Thank you. So actually, guys, look at this. So by the way, so you know, partition load is a gravity load and will always counteract the wind. Okay, but the thing is, when you think about it, sometimes those partition load, although we include them in our plans, sometimes we don't build them. So that's why the code here is kind of conservative. And if you read the statement number 5, which is part of the code and we have to follow, it says in case where dead load of the partition is counteractive, which is the case here. So that you can see the partition load is going to be added to the F and will be counteractive to the W, which is the wind. So in this case, the load allowance referred to sentence 2 and 3 shall not. Look at this, shall not. It means you shouldn't do that. Shall not. It means it's a must. Okay. And guys, remember also one of the things about the code, it's tricky. It's using the English. So when the code will say may not, it is different when the code says shall not. Shall not, it means a must. It means a designer shouldn't include the partition load in this case only. I'm not saying in general. I'm saying because this creates an exception. It means when the partition wall load is counteracting the wind load, please ignore it. Don't consider it because simply sometimes it's not there. So it's kind of a safer for us not to use it. However, I'm asking you, the self weight of the beam is, what do you think? Should I ignore the self weight of the beam, although the self weight of the beam is counteracting? No, because simply if the beam is there, there is a self weight. Okay, it doesn't go anywhere. Okay, dokie. So let's now, guys, since I said we have finished like the exception on statement number 5, then we can go ahead and read number 2 and number 3. Okay, a minute for you guys. Take a minute, read number 2 and number 3. Okay, so you know what? I'm gonna summarize. I know that you guys read number 2, number 3. I will summarize it. In number 2, it does make sense. It says if your current design drawing does not show or show a future partition wall, so you know the partition walls were not really built at the same time you build your building, which is by the way, this is in most cases or in some cases it happens. And some of you will say, how come? So guys, I've been in so many projects, and what happened is the owner of the structure doesn't have a tenant at the point when he decided to build the structure. Doesn't have a tenant, which means he cannot simply force the tenant for the partition, because simply by the change of the occupancy, then maybe the tenant will redo all the partition walls. So what they do is they will make a plan view, which is just showing the outside, and will leave the partition walls in the future when they have a specific tenant with a specific requirement for their use, then they will build it for them. Okay, so you can see in this case, partition we know is going to happen in the future, but we don't know the exact partition right now. In our design, we should include some allowance for those partition. Number 3, how do we estimate the load of the partitions? Is not very difficult. The load of the partition is simply what is the partition. So the partition can be a concrete like masonry wall. It can be just like a 2x4 with some gypsum board on both sides. It can be metal stud. It can be whatever it can be. So in statement number 3, it says the engineer or the designer shall determine the load of the partition based on the type of the construction of this partition load. However, this is something you have to be very careful. You can see here, it says here, shall not be less than 1 kPa. So which means if you do all the calculations and you found out the effect of the partition load gives you less than 1 kPa, there is a minimum that you have to consider in your design, 1 kPa. So if the partition load is 0.5, use 1. If the partition load is going to be 1.1, then use 1.1, don't use 1, okay? So 1 is the minimum. Statement number 4, I'm not going to actually because it's straightforward. Partition loads used in the design shall be shown in the drawing. So, and by the way, this is typically shown on the architectural drawing, not on the structural. They show all the partition loads. Now, number 6, which I'll give you a minute to read number 6. I think number 6, not sure if you had time to read, but number six is, it says, except for structures where dead load of the soil is part of the load resisting system, where dead load due to soil, superimposed earth, plants, trees is counteractive, it shall not be included in the calculations. Same guys, same as this example. Let's go back to the building. Let's say on top of the roof here, on top of the roof of this building, I have like a podium on the roof, and you know, there are some trees, planters, and soil. So should we include this in our design? Because when you think about the stability of the building, you can think about those as counteractive, and simply if they are counteractive, then in your design only when you think about the overturn of your building, then or turnover of your building, then do not or shall not be included. Okay, so let's move on to the next. And again, I think so far things are very dry, so that's why here I have like kind of some example by number. Okay, dokie, let's do it. So guys, on the left side here, I kind of picked this picture. So this picture on the left here is called roof assembly. So I bet you that you have been with us for a year now or over a year, and you've looked at some drawing in other classes like construction classes, and probably you've seen a very similar picture of a roof. So let's make it simple. I'm not expert, but I just came up with this one here. So I have a roof which has a concrete slab. So this concrete slab, and then there is a membrane that wraps around your concrete and the parapet. And on top of that, we have a rigid insulation. And then on top of that, we have like a plywood sheeting. And then finally, you have some gravel on top of that. So guys, when you think about it, I'm going to zoom in. You can see this picture here. It tells you all the component of the assembly. Reed place 200 millimeter concrete slab. We have membrane, 100 millimeter rigid insulation, and then I have 14 millimeter plywood sheeting, and then finally I have 38 millimeter of surfacing stone or paver ballast. Okay, so in this case, the example here is trying to estimate the dead load. So what is the dead load of this roof assembly? Guys, the idea here is very simple. So simply the dead load of this roof, number one will be your concrete slab. Number two, the weight of the membrane. So the load of every single layer. And on the right here, I kind of listed all the layers. So just copy this part to this side and simply come up with the weight of every single layer here. And then finally, the dead load will be, you just go ahead and add all of them together. Okay, I know some of you by now will ask, hey, Tahir, listen, how can we do that? How can we find the weight of the ballast, or how we can find the weight of a 14 millimeter plywood? I will go through this in details in the next slide, but for now, please just, trust me, and those are the numbers for the self weight or the weight of every layer and measured in kBA. So in this case, the total weight is 5.61 kBA. Guys, remember, I want to remind you, and I know probably all of you know that, kBA, it means kilo Newton per meter square. So which means a square meter of this roof, including all those layers, will simply is a 5.61 kilonewton, because that's the weight per unit area. Also, something I want to remind you that when we find or when we estimate the load intensity, there are two very popular units. One, you already know about it, which is kBA, kilo Newton per meter square, and the other one is called PSF, which is pound per square foot. You need to understand this relationship. A 1 kBA, so this one here is a 1 kBA equal to 20.8 BSF. And typically in my design myself, I don't use the 20.8. I make it easier for myself to remember, and I always use 21. So 21 is a good number. Again, so 1 kBA is approximately equal to 21 BSF. So for example, if you look at 5.61, so how many BSF this one? You just have to multiply times 21 and you will get around 100, it's more than 100 BSF. Also, something we will use in the next slide and the next part of our class is simply concrete density. Concrete density in there, okay? So the concrete density is, we call it gamma C, or gamma concrete. It is equal to 23.6 kilonewton per cubic meter. And again, for simplicity, again, I always make it easy for myself and my students. Let's use in this class 24. Very, very close, but this one is easier. So concrete density is 24 kilonewton per cubic meter. Now, let's go back to your question. I said, okay, Tahir, how do we, for example, find the weight of the ballast, the weight of the 14 millimeter plywood or 100 millimeter rigid insulation and membrane? This one, I'm going to go into details. This one, we have a special slide for it. However, those ones here, how can we find them? Here we go. The answer is here. Probably I need to zoom in. So guys, any construction, any manual, like for example, concrete manual or steel manual or wood manual, every manual provides the designer with the kind of material weight. I know that my slide right now is not really the best, and probably I have to kind of create my PDF one more time. I'm trying all the time to compress my PDF file, to the minimum, but obviously it came on the on the resolution of my PDF. So I apologize for that. I'm going to keep it, with highest resolution. However, if you do your best and look at this kind of table, you will see this table provides weight of different material like aluminum, brass, and stuff like that. And also on this side here, it tells you other information. For example, what is the weight of the gypsum board? You can see I'm gonna box it out here. So gypsum board is equal to 10 millimeter is equal to 0.28. You know what I'm gonna do right now, because simply it doesn't make any sense. I'm going to simply open my PowerPoint and simply teach you from the PowerPoint. Okay, because I have a better resolution in my PowerPoint. My apologies, guys. So I guess this is a better picture, guys. Now you can see this is a scan from the manual. So if you go to the concrete manual or the steel manual or the wood manual, you will see a very similar table. And the purpose of this table is simply to give a help for the designer to estimate some of the layers of your assembly, like the gypsum board. Okay. For example, probably you look at my cursor, you can see I'm going to point out some of the input. Guys, look at this, for example. Plywood is here. And you can see I have a 14 millimeter thick. And if you go to the end, it says 0.08. And the number is in KBA. And again, if you go one step up, here is your 0.08, the 14 millimeter plywood. And a very similar fashion, if you look at the table, you'll be able to get the weight of the 38 millimeter ballast, or the 100 millimeter rigid insulation, or maybe the membrane. Okay, but guys, I want to be clear with you. Not all the time, not every time you do a design and you're trying to estimate the weight of the roof assembly, you will find all the information you need from this table. Not really. Yes, this table is trying to give you a help for the most common material, but remember there are some new material. There are some material will not be listed in this document here. So what can I do? If I'm a designer or an engineer, I'm trying to estimate the load of the individual layer of my roof or floor assembly, and I cannot find the number in this table. What can I do? I myself will do a research on Google, will try to come up with a conservative number. And sometimes if you have a product, you simply go to the company website and then you look at the product sheet, and 100% on the product sheet, you will see, you will find the self weight of this product per square meter. Okay, so sometimes people, they create kind of insulated walls, and those insulated walls, which sometimes they are prefab, we know they are not listed on this table. Again, very simple, kind of 1-minute exercise. You go to the website of the company according to the name of the product, you look at the product sheet, and you find the self weight of this product. Okay, so again, don't ever think that this table will give you 100% of your answer. You should, or sometimes you will need to do some extra effort by searching the internet or by finding a specific manufacturer data sheet. Okay, now guys, there is a weight of the concrete members, and since we're teaching you concrete, and this will come our way almost every class, like what is the weight of the beam, what is the weight of the slab, what of the weight of the column. So that's why I kind of came up with 3 different slides to show you what is the weight of the concrete element. Okay, let's start. The first one It is called slab self-weight. So how do we estimate the slab self-weight? Not very difficult. So guys, remember the slab, if we know the thickness of the slab, and in this picture here, we refer the thickness of the slab as TS or T sub S. In this example, I used 250 millimeter, which means a 10-inch slab. Now the question is, what is the self-weight of this 10-inch slab? Very, very simple. What you have to do is you just multiply the thickness of the slab times the specific weight of your concrete. Guys, we agree in this class, we will use 24 as a simple number. Forget about the 23.6, 24. And if you multiply your thickness of the slab by the specific density or specific weight of your concrete, then you get the self-weight of the slab. The only thing I want you guys to pay attention to, it's kind of tricky and it causes some mistakes. Typically, the slab thickness will be given in millimeter. In my example here, it says 250 millimeters. However, when you try to find the self-weight of the slab, look at the units. If the specific weight of the concrete is 24 kilo Newton per cubic meter, looks like my slab thickness has to be in meters. So pay attention, and you can see in my calculations here, it is 0.25. So it's 250 millimeter, you divide by 1,000, so you turn it into a meter, then you multiply by the 24. So the self-weight of this slab is 6 kilo Newton per meter square, which is 6 kPa. Okay. Any questions so far? Any questions so far? Are we going fast? Are you guys following?
Good pace.
Thank you, sir. Okay. Thank you. Who said that?
Dominic.
1 mark for Dominic. Because you're my thermometer. I'm trying to get some, feedback, and you're my thermometer. I know that my bases go through. Thank you for that. Okay, let's go ahead and continue now. Now the second element, again, this is I'm trying here to show you how do we estimate the beam self-weight. My beam here is not steel. Probably by now you with Corwin knew how to find the self-weight of a steel beam, like a W beam or W section. This one is a bit different. This one is concrete. And I'm gonna go with the most common beam section. And I know, guys, if you have some experience, you will know sometimes my beams or the beams will be more complicated. Doesn't have to be a rectangular section. However, I can tell you in most cases, or very, 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 very common, the concrete beams are rectangular section because simply they are easy to build. When we get to the discussion of beams in details, you will see I'm going to show you other beam sections, but not really in building or housing. For example, bridges. When you look at the bridges and look at the bridge girder, typically it's not rectangular section. It is something else. And probably some of you have seen a beam or bridge girder. It doesn't look like a rectangle. Okay. Anybody to just for fun and for a mark as well, what is the shape of the girder of a bridge? Show your hands, please. No, nothing.
Can you show the picture, sir, again?
No, that's your observation. That's your observation on when you walk along the street and you look at the bridges. I myself, not a time I go around the structure and I don't try to understand how it's being built. That's something as an engineer, as a designer, it's just in my blood. Okay, so I'm just assuming that you guys in our program, and you start to love building and structures, and you try to understand and do the same thing. Okay, let's go with Hamid. Okay.
They're sort of like a T shape, sometimes a rectangle.
They are T-shaped. Actually, you know what? Like in bridges, I don't think it's a T-shape, but I'll give you a mark for that. It's T shape is a precast, and typically, and it's double T, it's typically in Barcade. When they build the Barcade, for example, the one in Chinook, the one in the west side of Chinook, you will see the Barcade made out of double T's. Okay. Now, anybody else to share with me what is the shape of the bridge girder? Let's go with Siham.
It's a trapezoid shape.
Trapezoidal?
Yeah.
No, I mean it's not trapezoidal. It is not trapezoidal. Okay, it is not. Okay. Thank you so much for that, Raymond.
Is it kind of like an eye shape?
Okay, perfect. So Raymond, you got 2 marks. It's true. So guys, when you look at the cross section of the bridge girders, it looks like an eye shape. But again, when time comes, I'll tell you why. But again, for now, let's go back, and so we kind of wake the class up. And so you can see in my picture here, as I said, this is the most common one. It's a rectangular beam where the height of the beam I'm referring to as H capital, and then the width of your beam as B. And then so the self weight, here is the equation. Simply, you have to find the area of the cross section, and then multiply it by gamma concrete. So B times H times gamma concrete. So if my beam is 250 by 800, so the width is 250 and the depth is 800. So how do we find the self weight of this beam? You just have to multiply the B times H times gamma. Again, one more time, be careful about units. Gamma is 24 kilonewton per cubic meter, which means both the width and the depth of your beam should be in meters. And you will get this number 4.8 kilonewton per meter. And guys, I know some of you will say, and this is a common mistake, so this is a common mistake. Some of you will say, Tahir, where is the length of your beam? Should we multiply by the length of your beam? So if your beam is 5 meters, should I multiply this number by 5? You do that only if you want to find the weight of the whole beam. But typically in our design, before we do the analysis, we estimate the weight per unit length. Okay? So that's why there is another dimension which is not shown here in this picture. It's a 1 meter. So we find the self weight of 1 meter beam. Okay? And we use this one as a uniform load in our beam in our analysis. Okay? So please do not multiply your beam by the length, this number by the length of your beam, because we are trying to estimate the self weight of the beam per unit length. Okay? Okay, now I think I want to stop here because that's a good point to stop, and we will break, and then after the break we'll continue with the live load. However, before I break, let me ask you, do you guys have any questions so far? Looks like Siham has one.
No, sorry, I just forgot to lower my hand.
Oh, never mind, that's fine. Okay, next is Hamid. Looks like Hamid has a question.
Yeah, I just have a short question.
Sure, go ahead.
Shouldn't the slab self-weight, shouldn't it be volume times YC?
Correct. I'm not saying correct. Look at this. Hamid has the same exactly what I warned you here. So I said do not multiply by the length of your beam. Just think about, we're trying to estimate 1 meter of this beam. However, also same concept applies for the slab. Okay, we're not trying to estimate the self weight of the entire slab. Okay, so we're not multiplying times L times W. We are trying to estimate the self weight of the slab per unit area, per meter square. Okay, so we take a meter by meter of the slab and we will try to find the self weight. Okay, did I answer the question?
Yeah, thanks.
Okay, let's go back and see if somebody else has any question. Okay, guys, if you have any question, you have. So we have Martin. Thank you so much. Come, Go ahead. Go ahead.
I'm just wondering, like, why are we not calculating the whole weight of the slab and just taking that little bit of it, like just the weight per unit length?
Okay, I think if I answer, probably the slab is very hard to answer right now, but I think for the beam I can easily answer. And I promise you, when time comes and you have enough information from my side to understand this, I promise you, Martin, I will give you the answer for your question. But I bet you if I answer, a kind of a similar question, you will get to know. Now, why? I'm going to make a very similar question apply to the beams. Why we do not find the self weight of the entire beam? So if the beam, for example, spans between columns as 5 meters, why don't we multiply 4.8 times 5 and we get the entire self weight of the beam? The answer to this is, look at this, please. And the answer is very simple. I'm going to go back to your to the assignment. So here is the assignment. Here is the assignment, and let's say, okay, look at this picture right now. You see this picture? Okay, you can see all the loads when we do the analysis on our beam, trying to find the bending moment and the shear and axial force. We simply load our beam with a linear load. Okay, you can see I'm not really interested to know what is the total weight. If I multiply 2 times 4, so this number is 8 is equal to the self weight of the beam between point A and point B. Okay, so that's not really handy when we do structure analysis. And that's why when we estimate the load, we try to estimate the load per linear meter on the beam, and then we place this load on the beam on SAFI to find the bending moment and the shear and axial force. Does it make sense?
Makes perfect sense. Thank you. That answers it.
And by the way, I promise you, when the time comes and you have enough information about slabs, I will promise you, Martin, I'll give you the answer for this, for your answer for that question about the slabs. Okay, guys, any questions
Thanks
so far?
very much, Tahir.
Oh, sorry, say what's again?
Just saying thank you very much.
Oh, no worries, thanks. Okay, any questions so far? Okay, if no question, I will see you guys at 8:58, 10 minutes from now.